to come up with a title and an abstract for my talk a while back. And, it was like probably 8 in the morning. And I decided this was a good title. It's a little bit corny. What I want to talk about today is the way that crypto is starting to become really important to application security developers and to software in general, but also the way software has begun to affect crypto. Probably the most famous example of that is Heartbleed. It's the only exploit that I know of that, my aunt and uncle can actually name right off the top of their head, although they call it the Heartbleed virus. So I sort of thought this was, we've passed a turning point, and I want to talk a little bit about what crypto is doing in this new world we live in. So for those of you who don't know me, which is probably a bunch of you, I'm a professor at Johns Hopkins. I teach computer science. I focus on computer security and applied crypto. I've been in the information security field for around 20 years. Years ago, I worked for AT&T Labs, and then I got a PhD, and I started a company. And so the really cool thing about my career is I've been all over the place. I've seen lots of stuff. I've seen lots of broken stuff. And I've also kind of been in the academic community. So I get the benefit of knowing, how we think things should work and how actually things do work. And it's kind of been a really neat career that way. The other thing I should mention is that my research mostly focuses on the way we can apply advanced crypto to real problems. And many of those problems are privacy problems. So for example, I work on anonymous cryptocurrencies and things like that. But many of them are just like, how do we make it a little bit easier to make crypto work in software? So let me give you a few examples of things that I've done recently that you might have seen, or maybe you didn't, but kind of define what I work on. So this was a project I worked on with my grad students last year. I was invited out to Apple about a year ago to give a talk. And during the course of giving that talk, I decided I wanted to say something specific about Apple's crypto. So I pulled down their design document, their iOS security guide, and I looked at how they implement the Apple iMessage text messaging protocol, how they do the crypto. And at about 3 in the morning, as I was writing my talk, because I always write my talks at about 3 in the morning, I found out that there was a bug in the way they were doing this. Many months later, this resulted in a news story. We basically were able to decrypt not every message, but every attachment message that was going over Apple's network, which is pretty huge when you think about the fact this is the first encrypted messaging network, and yet somehow they got the crypto wrong. So people make mistakes in crypto all the time. Another thing that I worked on recently, or a couple years back, was we actually just audited the TrueCrypt project. Those of you, some of you may know TrueCrypt. TrueCrypt is an open source encryption, file encryption program. It has a very sketchy history. In fact, there's some reason to believe that TrueCrypt was actually created by a guy who is now an international arms dealer and is in jail. So nobody knows who the TrueCrypt people are. We wanted to know if it was secure. So we took it apart and we looked. We collected money, and a lot of people gave very generously to do this analysis. And then most recently, I worked on a project where we came up with an attack called Logjam, which basically allows us to decrypt encrypted HTTPS or TLS connections. We were able to decrypt about 30% of them, including some that went to some really sensitive sites like the FBI, which was a fun project for me because I got to call the FBI and tell them their servers were broken. So that was kind of neat. Okay. So why am I giving this talk today? The reason that, I think crypto is so interesting is not because we can do neat things with theoretical crypto. I'm really interested in the way we can actually build real systems that use crypto to do cool things. All those cool things I read about when I read Cryptonomicon, years and years ago. But the problem is, as I've gotten further in this field, I realized that software people, particularly application developers, have a kind of a misapprehension about what we can do with crypto. And this is kind of promoted by a handful of statements you see on the slide. A lot of people think that, well, we have lots and lots of bugs out in the world of real applications. You don't need to worry about the crypto. The crypto is the solved problem. I think one of my most favorite quotes in this area is that cryptography is the strongest link in the chain. So stop spending your time worrying about the crypto. Just go off and worry about all those other things you can get wrong. So I really hate this attitude because it's wrong. All of these people are telling you falsehoods. We are not that good. There are many problems in crypto, and they really kind of run the gamut. So let me give you a view of what crypto, the big field of crypto, actually is. So crypto actually breaks down into a kind of a stack of different problems. Way up at the top, we have the one thing that cryptographers are really good at, and that's building cryptographic algorithms. So nobody is going to break AES tomorrow, and nobody's going to break curve 25519 tomorrow. We're great at building algorithms. But that's just the tip of the iceberg. So beyond that, we have stuff that we're continuously screwing up. We have protocol design. We constantly get this wrong. And I'm just talking about in the IETF and academic sense, we get protocols wrong all the time. And that's even better than what we do when it comes to actually implementing crypto software. We do a terrible job at that. And then, of course, ultimately, we build crypto libraries and software, and we want to share them with people who develop actual applications. The attitude in the cryptographic community has been, you guys, application developers should come to us. We will throw something over the fence, and if you want to use crypto, go for it. And the result of that has been some really, really terrible library APIs. And those APIs are probably contributing more to insecurity in crypto than anything else we do. And then beyond that, we have all the things we usually get wrong, which is actually convincing people not to do dumb things with crypto, to actually deploy it correctly. So really, we have one thing at the top that we do well, and I drew these little guys just to show kind of, how things get worse as you go down. Okay. So why does it matter? Like, why should you actually care about this crypto stuff? I mean, if you look on Twitter any day, InfoSec Twitter, you see 1,000 new vulnerabilities every week. And only a few of them are related to crypto. So who cares about this stuff? Well, the answer is we all care about this stuff because it's kind of getting worse. I mean, first of all, this talk is about Heartbleed. It's not really about Heartbleed, but the title is about Heartbleed. What was so special about Heartbleed that made it such a famous vulnerability? Well, Heartbleed isn't exactly a crypto flaw. It's a software flaw that happens to exist in the crypto stack. But the problem is the crypto stack exists really low down in a very dangerous place in many of our systems. And we rely on that crypto stack increasingly for all kinds of things. So when Heartbleed screws up all of our SSL servers, we lose all kinds of data and everybody has to revoke their certificates and bad stuff happens. Similarly, with bugs like go-to-fail. Does anyone remember go-to-fail a couple of years back? Where Apple made a mistake. They had an extra line in their software. And go-to-fail meant that like 1 billion Apple phones could have their encrypted connections intercepted. Now, intercepting encrypted connections doesn't seem like that big a deal. But when you've built software that depends on the idea that I can connect to a server and send a session token or something securely, and just utterly takes for granted the idea that secure network communication is possible, bad things happen when you start breaking down those assumptions because somebody screws up some software. And there have been many other examples of people getting SSL and TLS wrong. So these are the things we're supposed to be able to do right. Let's see why we can't do them. Okay, so another reason that this matters is because of slides like this one. This is a slide from Edward Snowden's documents, the document cache that he released back in 2013. It's a GCHQ slide. Hopefully none of you guys have clearances and are now going to be like locked in a room for the rest of the day because of this. But this is a slide that talks about somehow the NSA is decrypting, and the words here are really interesting, vast amounts of encrypted data, which have up till now been discarded, are now exploitable. I mean, what the heck is going on with that? That should not be possible. We, as the cryptographic community, have no idea what's going on there, and it scares us that we don't know what's going on there. Then there's a slide like this one, which talks about a project called SIGINT Enabling. What this is a top secret project to basically go to vendors and mess with their crypto and mess with crypto standards to make them broken. And they even talk about a handful of examples, a couple of things you probably can't see from the back, but they talk about inserting vulnerabilities into commercial encryption, IT systems, networks, and endpoint communications devices used by targets. And they even give examples, which I don't have on here, of actually backdooring VPN encryption chips. So this is bad stuff. We should care about it because the numbers here are huge. It's a lot of traffic being decrypted. If it's being decrypted by the NSA, maybe the NSA are the good guys, but how do we know it's not being decrypted by the bad guys as well? So when it comes to corporate espionage, this stuff may matter a lot. The last reason that I would say this stuff matters is because crypto is kind of becoming more and more fundamental to our lives. So increasingly, we encrypt the data that we carry around with us on smartphones, that we back up to clouds. And this has gotten to the point where we're doing such a good job of it. I'm not saying we're doing a great job. I'm just saying we're starting to do it well enough that people are freaking out about it. And of course, you know this guy. This is FBI Director James Comey. Some of you may have heard last spring about an issue that Apple had with the FBI over an iPhone. There has been a big debate about whether crypto is actually too strong and whether we need to put some kind of backdoor in to make it so that you can decrypt phones, decrypt backup data, and so on. So the good news is we're actually starting to do crypto well enough that we can freak out the FBI. The bad news is we're freaking out the FBI, and we don't know quite what to do about that and what the future of crypto is going to be. Okay. So that's kind of the setting for this talk. There are all these reasons that crypto matters. It matters to application developers, matters to the world. I hope I don't have to spend too much time convincing you this is important. What I want to do in this talk is really talk about different ways that we get things wrong. I want to talk about how cryptographers have kind of made mistakes that led to bad stuff happening to everybody. And I'll spend a bunch of time on that in really important protocols that you all rely on. I want to talk about how we're screwing up our software that we give to people to implement, and why that's led to a lot of vulnerability and how we can try to fix that, or maybe point in the direction of fixing it. And then I want to talk about how people who develop applications and actually write software, are contributing to this just by writing software, which is kind of always a bad thing. So, all right, so I want to spend a bunch of time talking about a specific class of vulnerabilities, just to give you an illustration of how far behind we are in actually getting crypto right. Okay, so how many of you folks know what SSL or TLS is? Good. Most people, when they encounter SSL or TLS, don't even know the word SSL, TLS. They just know, hey, if I see a lock on my browser, I see HTTPS, that means I'm using a secure encrypted connection, and presumably nobody who's running the Wi-Fi access point in this hotel can see what I'm sending over that connection. They can't intercept that connection and insert JavaScript or other bad stuff. In fact, from an application developer's point of view, it's fantastic, because all you need to do, if you have a good crypto library, good system, is basically make sure that if you're doing web hits, you're doing it over the correct URL. And presumably everything else happens from there. Does everything else happen right from there? Always. Not necessarily. Okay, but in theory, we have to make sure we're using secure connections, and then everything should work from there. Okay, so I want to give a little bit of a history of the SSL TLS protocol. By the way, it has two names, and I'll explain why in a second. So SSL, Secure Sockets Layer, was born at Netscape Communication Company, whatever it was called, back in 1994. We have no idea what the version 1 of that protocol was, because it was so bad they never released it. Then, about a year later, in 1995, they released SSL v2. That was the first version of SSL that was ever released on the internet. Do we still use SSL v2? Of course we do. Yes, absolutely. There are tons of servers running SSL2. In fact, there was an attack earlier this year that relied on the fact that servers were still running this crappy protocol from 1995. Then eventually we improved it. We got version 3. And Microsoft in 1998 said, you know what? We're willing to implement this thing, but only if you change the name to Transport Layer Security. So we changed the name of the protocol, and then we went on. The newest version is from 2008. It's TLS 1.2, and we're about to get a new version sometime in a year or so called TLS 1.3. Great. And the only reason, by the way, that we've gone to point releases is that everybody is terrified of going to TLS 2.0 because they think a whole bunch of people like Microsoft will ask for like new features, and they figure if we just increment by a point, it will be better. Okay, so there's a reason that I have a picture of Will Smith on this slide, and the reason is that for those of us who grew up in the 1990s, these dates for SSL 2 and 3 don't seem like that long ago. The 90s, to me, are just like yesterday. However, when you look at Will Smith, you can see that the world around us has changed. And actually, the world of cryptography has changed too. We've learned a lot of things since the mid-1990s that we didn't know when we designed these protocols. Unfortunately, because there's a lot of backwards compatibility requirements in building protocols, we're stuck with many of the bad things. Okay, so how secure is this TLS protocol we're building our internet on? Well, we know that there have been a bunch of kind of active attacks and vulnerabilities and implementations. Of course, the most famous one is Heartbleed. That got patched after it freaked everybody out on the internet. But there have been more subtle ones that are harder to exploit, but they've been real. One of them is called Lucky 13, which was about using timing channels to break cookies out of things. A lot of these are exploiting TLS to get cookies. There was one last year I'm going to talk about called Freak Crime, which used compression, all sorts of things. People using the RC4 cipher in 2016, which is terrifying because RC4 is a terrible cipher. So we're constantly reading about these kind of vulnerabilities in TLS, which usually get fixed before things get too bad. Okay, so why do we have all of these problems? The person who is in charge of the TLS 1.3 protocol is a guy named Eric Rescorla, goes by the name Ecker. And the best description I've heard anyone use is that the problems in TLS result from the fact that we're using prehistoric cryptography. I want to point to one or two of the worst things. You don't have to know what all of these things are. One or two of the worst things is the thing at the top, this export-grade encryption. So back in the mid-1990s, we being whoever designed SSL, decided that in addition to strong cryptography, we needed to have some weak cryptography in there as well. And you probably know why we did this. The name implies it was for export. We didn't want people overseas to have software with strong crypto. Now, thinking about this for about 5 minutes, you can see what a stupid idea this was, right? Like, how are you going to prevent people from downloading software? But we tried. We tried up until about 2000, 2001. And the idea was that if you downloaded a browser from overseas, I think it wasn't even that it would check your IP address. You would say, I am not a US citizen. And you would get a browser that had 40-bit symmetric encryption keys and would have 512-bit RSA keys, which somebody, presumably at the NSA, decided was strong enough for your credit cards, but not strong enough that it would keep them out of intercepting your connections and decrypting. That must have been the justification. So we have these export ciphers. Now, of course, if you ran a server and a browser in the US, you would get strong crypto. And so we had to build our systems to support people coming from overseas and from inside the US, and we had to handle all of these different things. It got really, really painful. We had to develop this whole notion of having different cipher suites so we could actually switch crypto on demand. Okay, so these things were really terrible. Now, the good news is the laws were mostly changed in 2000 to make export crypto unnecessary. Okay, so it's many years later. We should not even be thinking about export crypto, and yet export crypto lives on, as I'm going to show you. Now, I want to dive into the internals of the TLS protocol, and I want to show you what actually happens when you make that HTTPS connection up to a website. So there's a process that we run that's called cipher suite negotiation. The person on the left, Alice, is your web browser, and the person on the right, Bob, is Amazon.com. So you're going to go and you're going to make a connection. The very first thing your web browser does is it says, here are the encryption algorithms that I am willing to support. And in this case, we're going to give RSA, which is pretty strong, DHE, which is Diffie-Hellman, pretty strong, elliptic curve Diffie-Hellman, and, oh well, we might as well throw in this RSA export cipher suite, which still exists in 2015-16, despite the fact that it's totally crazy. So we'll offer that as an option. Now, normally what's supposed to happen is your web server, assuming it's sane, is going to pick the one it likes best, which is not going to be a broken 1999 export cipher suite. It's going to pick, I don't know, elliptic curve Diffie-Hellman. It's going to then do a key exchange and make sure you have a key shared with the server, and then it'll confirm after the fact that nobody tampered with those messages that went through in the first move. So this is the whole process. This is roughly the entire protocol. Great. So what happens when you've got a bad guy operating your Wi-Fi access point? By the way, Thomas Potacek made this for me a few years ago, this symbol. I've really appreciated it since. It's really helped my presentations. Everyone should use it. Okay, so what happens is this. Remember, your web browser's offering all of these possible cipher suites, but we're sending it over an insecure Wi-Fi connection, and your attacker can edit this message. And they do something very simple. They just cross out all of the secure cipher suites that you would normally pick, and they leave the insecure export one in the message. And that goes over the wire to the server, and of course the server only sees that you support the insecure one, so it picks it. Great, now you're using a 512-bit RSA key. Does anybody know how long it takes to crack an RSA key, 512-bit RSA key today? About an hour, I'd say. About an hour on EC2. You need to use a bunch of computers, so it's not trivial. It takes about an hour, and it costs $70. Okay, so this is kind of bad. Would be bad if we were using one new RSA key per connection. But actually, the keys get generated when the server starts up. And so basically, with these 512-bit RSA keys, if your server stays up for a month, you just need to crack one key, and you can intercept every connection that goes to that server if you can edit the messages going over the wire for, until that server crashes. And so this stuff does happen. Now, the good thing, skip some slides. Now, the bad thing is it would seem that export encryption, 15 years after we got rid of the need for export encryption, nobody out on the internet would be supporting it. Unfortunately, it turns out with some internet scanning, as of last year, we found that about 30+% of the servers on the internet were still accepting RSA export encryption. So this was a really surprising and really bad thing. And among those sites that were supporting export encryption included some really cool sites like NSA.gov, which was fun, and FBI.gov, and also a site that you guys probably don't think about very much called connect.facebook.net. Now, if you know what connect.facebook.net is, it is the site that Facebook uses or used to push out its like button to all of the web pages on the internet. So basically, it serves JavaScript onto 90% of the pages you visit if you visit in a normal day. So if anybody can intercept that connection, they can insert malicious JavaScript into your page context, and then you're down to whatever protections your browser might offer against that. Who knows what those might be. So this was a pretty bad thing that these things were offered. All right. Now there's good news. I will move through this quickly, but there is good news. Most modern web browsers, the Alice's, the people on the left, will not offer to use RSA export. So Chrome will not say, hey, RSA export is one of my options. Firefox won't do it. Internet Explorer, Edge, whatever, won't do it. Unfortunately, there were two clients that used it a lot. So one of them is wget, and the other is curl. Now, how many of you, in implementing any kind of piece of software, have said, you know what, I need to download some file from a link. I'll just use curl or wget and call them on the command line. Show of hands. Okay, like everybody, come on. You've all done this, right? I just looked at a piece of software recently that was downloading its software updates using curl, and it was a version of curl that was vulnerable to this. So yes, these things happen, and it meant that anybody who was on your Wi-Fi or controlled your network connection could basically serve you. They had no other protections. They could serve software updates of their choosing. So this stuff happens. So that's bad. But still, if we just focus on modern browsers, modern browsers typically do not offer these export cipher suites as an option. So here's what a modern browser will do. It won't say RSA export. So we should be safe, even if the server supports it. Turns out that there was a bug in OpenSSL, in Secure Transport, which is the SSL library used by Apple, and in Microsoft's S channel. So pretty much every browser in the world had a bug in it. And what the bug did, NSS too for Firefox, what the bug did is it allowed this attacker, even if you didn't offer RSA export, to add RSA export as an option to what the client was asking for. And when the server got that, it would pick RSA export. And because of this bug, the client would accept the export grade key anyway, even though it didn't ask for it, which is a really weird bug. And the question you should be asking is, how did 3 separate implementations of this protocol end up with the same bug? Does anyone have any theories on that? I'm actually curious. How is it that Microsoft, OpenSSL, and Apple, implementing this protocol separately, screwed it up in exactly the same way? What's that? It's very possible they were all using the same test suite. Yep, that's true. So one possibility is they just copied each other. That's my theory. But the other theory is that it turns out that there is no one protocol. There's TLS 1.2, there's SSL 3, there's TLS 1.1. And when you're implementing all of these different protocols, there's an instinct to kind of save space and build one big state machine that covers all of these protocols. And when you do that, what you're actually implementing is like a meta protocol. That's not TLS 1.2, it's not SSL 3, it's like the combination of all of them. And so another theory is that what happened is by implementing all those protocols in more compact code, they created a new protocol that was vulnerable to this thing where export keys would be accepted even when you didn't ask for them. But it was really a kind of a devastating attack. And I want to show you a picture of this. Now, it may be a little hard to read there, but the site up at the top is www.nsa.gov. This is their employment page. And what you see here is a certificate. Oh, it's very blurry, sorry. What you see here is a certificate that is a valid certificate for NSA.gov. And yet, clearly, the text on this page is not NSA's employment page. It says something like, are you sure you really want a job here? So clearly, if the NSA can't get their crypto right in 2015 because of these bugs that we put in TLS or SSL, this is a bad thing, and cryptographers should be really awake to that. Now, the good news in the story is that we were able to get a lot of people to fix it. So the browser vendors fixed it, and so on. The bad news, and I'm going to skip a few steps here, the bad news is that many of the fixes that we asked them to make, they couldn't implement. And the reason was, when they scanned the internet, they found that 3% of the internet would have been broken if they implemented the fixes they needed to make these attacks go away. Now, there's another attack called Logjam that was related to this. So the problem we have is there's so much broken stuff on the internet now that we can't patch bugs in some sense, because we would break a lot of people's internal websites. So it's hard to patch these things. We need to patch them because if you don't patch them, the whole internet's broken in a sense, but it's very, very difficult to convince browser manufacturers to make these changes. Okay, so this thing was called Freak, by the way, that I just talked about. And a bunch of people finally issued patches. It took months and months. Okay, so I hope, just given this little taste, I've convinced you that cryptographers kind of suck, that we're doing things wrong, and we're trying to get things right. We're just getting to the point where we know how to do things a little bit better. But we're not great at this. Okay, so now I want to talk about where we do even worse, how we interface with software and application developers. Okay? So many of you have used cryptographic libraries. How many of you have used a cryptographic library? How many of you have implemented something using OpenSSL? Wow, that sucks. How many of you use NACL? Oh, that's too small a number. Okay, all right, we'll come back to that. All right, so typically cryptographers, very rarely do cryptographers and cryptographic engineers build actual applications. What we like to do is we like to build libraries. We say, here's a library, here's OpenSSL, here's a thing called, what is it, the GNU one, libgcrypt or whatever. We throw it over the fence and we say, you guys, you need to do something, you need to hash a password, you need to connect to a web server, you need to encrypt a blob of data. Use our library and it will take care of all your problems. So but the problem is we don't actually develop those applications, so we don't really know how to do it well, or at least we haven't bothered. And the problem is we mostly aim to other people like us. We don't think about who is actually going to use our software. And this is a problem, or it wasn't a problem back in 1999, or 2000 when most people developing crypto software were kind of crypto nerds themselves. But it's a big problem now that everybody is tacking crypto into their applications and bad things are happening. Okay, so we end up with bad stuff. And unfortunately, the bad stuff continues to proliferate because there are new libraries or new APIs, like the Web Crypto API, which is now going to be available in browsers, which basically are making the same mistakes we made back in the 90s, but they're pushing them into the modern era. So we have all of these bad interfaces, and people are kind of getting stuck with them and getting hurt. So I want to give some software examples. And I want you to see what I'm talking about when I say these things are bad. Okay. So here is an example of code. Don't worry if you can't read it. You're not meant to read it. This is code that uses the OpenSSL crypto APIs to seal or encrypt a blob of data and write it to a file. Now, what do you notice about this code? Is it attractive? Is this code that you want to audit and try to deal with yourself? Hopefully not. It's terrible code. It's extremely complex, and some of the functions read like EVP, PKey, assign, RSA. It's not even clear what they do. It's very complex just to write anything using this code. So there's a lot of complexity just using the libraries that we have today. Unfortunately, the directions for using these libraries are just as bad. And just in case people back there can't read this from all the way back there, let me give you some of the instructions. Under no circumstances be tempted to get the IV anywhere other than from rand bytes on the encryption side. Don't set it to a fixed value. Don't use a hash function. Don't use the recipient's name. Don't read it from disk. Okay, actually, these are pretty good instructions. I take it back. But the point is that in order to use this crypto stuff right, we have to yell at people. We have to say, don't do this thing that we know people do wrong. Don't do this other thing. Don't do this other thing that other people got wrong. So unfortunately, these libraries are pretty hard to use. This is my favorite. Do not omit error checking. If a function fails and you ignore it, it's quite possible, even likely, that your system will appear to be functioning normally, but will actually be operating completely insecurely. Who the hell designs a crypto library that works like that? It's mind-boggling that we could build something that would let you set it up wrong and then would just spit out plain text, and yet we routinely do this with crypto libraries. It's a very big problem we run into. Okay, so another thing that we get wrong is we let people, and I'm sorry, but we let application developers, we leave them. Let me rephrase this. It's not that we let people pick their own algorithms. It's that we put people in a position where they have to pick exactly which crypto they're going to use. And picking crypto sucks. It's very easy to make one wrong decision that gets everything wrong. The best example of this is unauthenticated encryption. If you are ever in a position where you have to encrypt something and use, let's say, Java. Java loves to give you options like AES. Okay, what are you doing when you encrypt with the AES mode? When you set up, java.cipher.whatever AES? Does anybody here have any idea? Sometimes, yes. So you're using either a bad cipher mode that's not even secure. Other times, depending on the Java implementation, you'll get something totally different. In fact, it's not defined. A lot of the time, it's not even defined. You don't know what you're getting. But most of the time, it's something totally insecure, like ECB mode. So very often, people find pieces of code on the internet. They say, I need to encrypt a blob of data. I'm not going to spend a lot of time learning about this. I'll copy something off Stack Exchange. And next thing you know, they're doing unauthenticated encryption, or they're using ECB mode. And actually, it's really easy to decrypt ciphertext in some situations when you use that kind of crypto that's not secure. Or they end up using something like RC4. RC4 is my favorite crypto algorithm because it's the only crypto algorithm that I can copy off of Wikipedia and get working really quickly. Like, it's 5 lines long. The problem with RC4 is it's really insecure, so you shouldn't use it, even though it's 5 lines long, which is really awesome. Okay, then they do other stuff that's really stupid. And then there's all this emphasis on legacy applications. I want to point to this paper down in the bottom. So there is a standard by the W3C called XML encryption standard. Turns out to be completely broken. If somebody encrypts XML using the standard according to the way the standard is written, then you can go to a server that decrypts, and you can byte by byte decrypt everything in the encrypted message if you intercept it. It's really that bad. When researchers went to the committee and they said, look, this is a problem, you guys, the standards committee said, you know what? We're going to add an optional mode that fixes this problem. And the researchers said, optional? Why isn't it mandatory? Why is this not the only way it works? And they said, well, a bunch of people have already written code to it. We don't want to mess up their code. So a lot of the time we get stuck with these legacy applications where you can't change things to make them secure because people have already written that code. I'm going to skip over, well, I'm not going to say anything else except that if you are ever tasked with encrypting something with RSA and the words PKCS v1.5 come up, PKCS number 1 v1.5 come up, run away. Like, that is a really insecure algorithm. There have been attacks upon attacks upon attacks that take advantage of the fact that that algorithm is insecure, and yet people still use it, and we still put it into new standards. OpenSSL has bugs because of it. It's terrible. And these things were invented in the 1990s before we knew any better. But we still offer them as options to developers who shouldn't have to make these decisions. Going on and complaining about APIs some more. I already complained about Java, but there's no reason to not complain about Java more if you're given the opportunity. Okay, so here is the Java crypto API. This is the java.crypto.cipher API, and you're basically allowed to pass in what they call a transformation. It can consist of 3 things. You can't really see it back there, but one is algorithm, mode, padding. Most people don't even know what that means. Or you could just say algorithm. And what the comment says, in the latter case, provider-specific default values for the mode and padding scheme are used. The problem is that providers differ and you have no idea what you're going to get, and oftentimes it's pretty terrible. So if you just say AES, bad things are going to happen in code. Now, do people just say AES? Well, here's a search, I think, of GitHub. Just do it now. Go and find a code search tool and search for anything that instantiates cipher.getInstance, quote, AES. You will find thousands and thousands of results. If you restrict your set to just things you care about, like applications you might conceivably use someday, you'll still find hundreds and hundreds of results. People are doing this all over the place. And unfortunately, it's because we've made bad APIs. Okay, I want to talk about one of my favorite API interfaces because it's a Microsoft interface. And because, like all Microsoft APIs, it's impenetrable. Okay, this is called Certverify Certificate Chain Policy. Who wants to make a guess at what this does? I don't even know what it does. It doesn't matter. It basically, you give it a certificate, and it verifies that the certificate chain is correct using some kind of magic that Microsoft implements. Okay, so it seems pretty straightforward. You kind of pass it some stuff, and it says, okay, is the certificate chain I got from a web server actually a valid certificate chain? Yes, probably. Okay, we're good to go. Now, again, probably hard to read from back there, so I'll just read this out loud. The return value indicates whether the function was able to check for the policy. It does not indicate whether the policy check failed or passed. Who writes this API? Like, what in the world? If the chain can be verified for the specified policy, true is returned, and the DW error member of the P policy status is updated. A DW error of 0 indicates the chain satisfied the specified policy. How many of you think any developer has, well, maybe a developer at Microsoft has gotten this right, but people routinely screw this up. Because again, who would think that you have to check for multiple values inside of structs to see if something that is important as, is my web server who I think it is actually verified, because that's the thing we're checking here. Last one. I hope this is the last one. My favorite interface that people constantly run into. People use libcurl, or they use the curl command line tool. One of the best things about this is the return value from curl. It's very similar. It basically, not the return value. You can tell it whether or not to verify, if you go to Amazon.com, to verify whether you're actually talking to Amazon.com. Now, you might think that's kind of something you'd always want to verify, but apparently this is an option you have to flag in curl. So there's an option, there's a flag. So you can say 1, which means check to see if the server has a name. Not the name you want to talk to, just a name. Or if you want to make sure the server is actually Amazon.com, you have to say 2. Now, who knows that you would have to specify 2 as the input to a function to verify that you're actually making a secure connection, and yet this was actually the API. I'm not sure if it still is, but this is one of the APIs people use. Now, the reason this all matters is a couple years back, a bunch of researchers decided, let's see how badly people are doing at this. So they built a bunch of automated tools that scanned Android apps. They went through the entire Google Play Store and looked for people building Android apps that were not checking that they were connecting to the right server. And they found that something hideous, like some large percentage, like half of the apps that they scanned, were actually willing to talk to any web server, whether or not it was actually the web server they were supposed to connect to, as long as it had a valid SSL TLS certificate. So in other words, if I go to talk to a server that says Amazon.com and it comes back with evil.com, but it has a certificate for evil.com, my application is cool with that. Any notion of why that might be the case? Why do people break their application so they'll talk to any server? They talk securely to any server, but not with checking it's the right server. Exactly. Some huge percentage of some of these things were because the APIs were confusing and people screwed it up. But the vast majority were that people were testing. And you're developing your code and you're like, crap, I don't have an SSL certificate on my stupid server, so I'm just going to turn the verification off, and then you push code, it goes out into the world, and then all of a sudden you have a million apps that will just talk to any server and can be trivially man-in-the-middle and intercepted. So this stuff happens all the time. And, again, there should be some way that as library developers, we can make this easy and safe for you to do testing without things being so dangerous in the world. I'm not even going to talk about this. I have no idea what's going on there. Okay, so what in the world do we do to fix this? I don't have a ton of examples because sadly, as cryptographers, as cryptographic engineers, we don't have a ton of good responses for this. Probably the best direction we have is a set of libraries. The one that I want you to come away from this talk knowing about is a library called NACL, N-A-C-L. There's also another version of it called libsodium, which basically makes the build process a little bit easier, has a few extra functions. What's beautiful about this is if you ever find yourself in a position where you need to encrypt some data, there is, instead of saying, okay, I'm going to write that code I showed you way back at the beginning, where we use EVP, PKey, seal, blah, 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 you have a single function called CryptoBox. And CryptoBox takes in a bunch of strings. It takes in a string public key. It takes in a string, you can take in a secret key for the person, your secret key for the person you're sending, the public key for the person you're sending to, and a nonce, which is just a random value, and the message you're sending. And it takes in those very simple inputs, and it does all the crypto without making you make decisions. And it does it very securely. This is written by Dan Bernstein and Tanya Lange and a bunch of other people. So we do at least have some tools that let us do crypto pretty easily and pretty securely if you're willing to move to better libraries and not be backwards compatible with some old stuff that used, RSA PKCS 1.5 from years ago. So we know what direction we have to go to. We're just trying to build the tools that get people in that direction. Okay. So the last thing that I want to talk about, and I'm going to talk about this very briefly, is how commercial software is getting crypto wrong. Now, you all have seen graphs like this. This basically shows, I think, the number of CVEs in software. Unfortunately, this only goes through 2012. So we know that we're not doing very well at software. I'm not sure why things got better in 2011, 2010, whatever, but we know that we have a lot of bugs in our software. So this is not news. You might have seen this chart, which is also a couple of years out of date. This is prices for buying exploits in various operating systems and software packages Sadly, Adobe Reader is not very expensive. iOS is way down there at the bottom. That gives us at least an idea of kind of what the demand is and how secure these different operating systems are, but we know that people can penetrate pretty much any operating system. Now, how exactly, does this affect crypto? Well, first of all, if somebody can break your software and compromise an endpoint, most of the time crypto is not going to really work. So we shouldn't worry about that. But then there are cases where it does work. So for example, when the Apple iPhone that the FBI wanted to get into last year was encrypted, it was not trivial for the FBI to exploit it. They actually had to go and pay $1 million to find an exploit that would get them into the kernel, would let them break the crypto. So there are cases where it is pretty hard to exploit crypto, and this stuff really matters a lot. So the example that I want to give that is probably at least the highest in my mind right now, of people doing really, really scary things with crypto, comes from a recent incident that involved Juniper Networks. Hopefully nobody here works for Juniper Networks. Okay. So it's not only the case that we have to worry about people making mistakes with crypto. If we buy commercial crypto software, and you remember that slide I showed you early on in this presentation that talked about the NSA inserting vulnerabilities in crypto, we now have to worry about the possibility that someone who doesn't have our best interests at heart might have tampered with the crypto software inside of a box to make it vulnerable. And we had a really, really compelling example of this last December when Juniper Networks announced a CVE that allowed you basically, for a knowledgeable attacker who could monitor VPN traffic from a NetScreen box, to decrypt that traffic. And it turned out that the reason this happened was because some hackers got into Juniper's code and they altered a 32-byte value in the code to make it so that they had a master trapdoor for every single connection made by a Screen OS device. We don't know why they did that. We don't know what their target was. We certainly know that they had a reason for doing it. It was not an accident. But the really scary thing about this vulnerability is not just that some hackers got into Juniper Networks. It's that the architecture that allowed for hackers to add a backdoor was already in place inside of Juniper's devices. In other words, Juniper had built a system based on a hidden random number generator that allowed you to have a master secret that would allow decryption of all trapdoors, and they built that in themselves. The only thing the hackers did was they took the key, the lock, out of that system, and they replaced it with their own key. And as a result, instead of somebody at Juniper being able to decrypt all connections made by NetScreen devices, now these hackers were able to do it. So the lesson here is that in many cases, if you use software that you don't actually review, or you use a device that has software you can't actually see, oftentimes you will wind up with software that is either accidentally subverted or deliberately subverted, and this is really scary. The only other point I want to make on this, and I know we have a coffee break coming up, so I'm going to stop in just a minute, is that sadly, even if you are not just worried about devices being broken deliberately, this Juniper thing that I talked about, we have to deal with the fact that many devices out on the internet are broken because they're old. So many, many devices out there are using crypto and using software that is like 10 years out of date. And this hurts us all because the internet's a very connected place. When you have a large percentage of devices that don't work right, people have to bend over backwards to deal with this. And as a result, many things that could be fixed elsewhere in the stack don't get fixed. And so we end up with whole big chunks of broken internet that can be used to do all sorts of bad stuff to us and slow us down. We don't really have a solution to this. Hopefully, we'll come up with a way to make this kind of thing start working right. So this is a problem we have to deal with. Okay, so to wrap up, so you can all go and get coffee, this is my really compelling conclusion to this talk. Crypto is hard. It's hard to write applications to deal with. It's hard to design. It's hard to write libraries. Everything sucks. And I'm sorry that's the depressing lesson that I have to leave you with, but we are trying and trying to get better at this. And the great news from things like Heartbleed and all of these recent vulnerabilities is that it's made us at least start paying attention to the problem and trying to improve it. So in the next 10 years, hopefully you guys will all have better tools to work with, and maybe things won't be so difficult. So thank you all. Appreciate it.